Hello guys, welcome to this tutorials in which we will be continuing our discussion from where we left in our last time. See, earlier in the last tutorial section that we saw, we looked at CNNs. So we understood how we can tackle the idea of classification using CNNs, image classification using CNN. For that we used a specific data set, which is MNEST. We looked at the training and then the evaluation. The evaluation metric that we have used, since the data was balanced in that case, was a straightforward accuracy. You can, as I recall, so I just said that you can use precision, recall, F1 score, AUC, RUC curves and all those things. So you can go ahead and look into those aspects. So from there we shall continue. Now in today's discussion we will be looking at sequences. Okay. So I am assuming that all of you are quite comfortable with the idea of sequences. So wherein which we have a temporal data. Okay. So now let us start discussing on sequences and how do you tackle the problem of sequences, handling sequences by using recursive neural networks, RNNs, or the upgraded versions of them, which are LSTMs and then GRU. So now first let us create a sequence. Now I am creating a sequence of batch size 4. Okay, I am having 4 instances. So now I have here I will just prefer to go ahead with x1, which is the first one, x2, x3 and x4. I have 4 instances, 4 examples, and each example is having a sequence length of 5. Okay. Now that means that this x1 now will have x11, x12, x13, x14, x15, something like this. Similarly for the remaining, and each xij which is there belongs to R3. Now this is what is our setup that we have as of now. Okay. Now you can see here I have a batch size of 4, I have 4 examples and each examples have 5 temporal entities, 5 things, and each of those T is having is in R3. Okay. Now like that you create an X which is of that specific shape, where in which the dimension 1 is batch size, the dimension 0 is batch size, dimension 1 is the sequence length and dimension 2 is the input dimension. So now once we look at this, now sequence input shape, it is 4, 5, 3. Okay. So now let us proceed. Now let us look into the idea of RNNs. Okay. Now how do we tackle this problem of understanding sequences? Now we use the first one, which is the recursive neural networks, RNNs. So now we use NN.RNN. So in going ahead and defining it, okay, now since I am running it for the first time, I should have okay, since it is a sequential thing, should have gone there and got the PyTorch basics. I would have gone here and ran this first, which is all the libraries, and then obtain the GPU, since I am doing it for the first time, so that I can continue from there. Okay. These are the things that we already have seen. Okay. Okay, MLP, CNNs, okay, CNNs. Okay, yeah. Now we are here, we just ran this, we have created a tensor. So now let us look into the an RNN. Okay. So the input size, now that is each xt, what is the so the RNN will go ahead and what do you call process each timestamp, the input of each timestamp t at a time. So each of them is of size 3, and then that you are transforming it into an 8 dimensional space. So, like that I have how many layers of RNNs you have? You are having only one layer of RNNs. Now, always, now whenever any transformation happens, the first indices, that is the 0th, so when you use that shape, dot shape, the first one has to be batch. Now, that is what this batch first actually means. Okay. So, now let us look at how does this RNNs work. Okay. So, now let us look at this recursive neural networks, RNNs. There, now x t which is there, say I am not using any superscript. So, just to indicate that anything you can look at it, x is in R3 and any h, the hidden state that you have will be in R8. Okay. This is what I am saying. So, how does this work? So, you have ht is equal to, now preferably we use tan h of weight that is associated with x into x at that specific instance plus weight that is associated with respect to the h, which is the hidden state, into the previous hidden state plus a bias term. Okay. So, now see, now since I have fixed ht to be R8, now I have to perform this operation in such a way that the output now has to be a vector of size 8. Okay. So, now let us see that how does it work into picture. So, now this you have this xt. So, each xt is of size 3 cross 1. See, this you have to transform, see whenever you are adding, all the 3 terms should be of the same dimension. So, this wx will be of size 8 cross 3. The ht minus 1 will already be of size 8 cross 1. Okay. So, now this will be of size 8 cross 8. Now, this will be a 8 length bias. So, now the outcome will be, this is 8 cross 1 plus this is 8 cross 1 plus this is a 8 length vector. So, now you can go ahead with that, and then tan h is performed individually on each of them. So, therefore, the hidden state, the updated hidden state that you have ht is coming to be an 8 length vector. Now, this is what is being done in this specific RNN cell. So, now then what happens here? Now, you can remember, now if you have an RNN cell, okay, now you get h0, now which belongs to, which will be a 0, to that you give x1, okay. Now, you give x1, now that will give you h1, and then again you use the same RNN cell. What do you mean by use the same RNN cell? Now, I mean that use the same weights and biases, okay. Now, then the same RNN cell, now you give x2, now this will give you now h2, so on and so forth. You repeat the same thing, and finally you have h n minus 1, go here, you get h xn, okay. Now, this is what the whole processing is. See, normally what happens is, at an each cell you can get an output. Now, how do we do that in the cases is, now y at any instant t, now what do we do is, now we use a weight why, okay. So, to that ht plus by. Now, we do this operation so that at each output, now this you get y1, this you get y2, similarly you get here yn. Now, this is how the standard RNN will work, okay. That you can see here. Now, you are going ahead with 4, 5, 3. So, 4 is the batch, 5 is the number of sequences, 3 is the size of each one of them. So, the output, okay. So, this is y. So, now whenever you, this returns 2 things, as you can see here, one is the output, the other is hidden. Now, output, what is this? When I mean output, in this case, what does it mean is, you get y1, now y2, so on till yn. This is what will be the output, and when we say hidden, now that will be h1, h2, so on till Hn. Now, this is what you will get as the output and hidden. So, now we can look at the shape of x is 4, 5, 3 and then y will be for each of those 4 examples, for each of those sequences. So, you will have 5 sequence in each example, you get a 8 length output. This is your y, now which is this output, and then this hidden now which is there for each of the 4 examples you get the 8th length vector. Okay. Now, this is the overall way of working. Okay. This is RNN, and similarly now let us look at the LSTMs. Okay. So, now let us bring in the idea of LSTMs. See, the reason why we needed LSTMs was the problem of vanishing gradients. So, here now we have a couple of transformations. There is some popular version, the way in which this is being discussed now, which is you have this what is known as the forget gate, you have this input gate, we have this candidate gate, and then we have this output gate. Now, these are the 4 different transformations that are there. Okay. See, unlike RNNs, now wherein which you only get one state as the output, now here now we will get 2 states as output. Now, one is this HT, now which is called as the hidden state, and then in addition to that we get the CT, now which is what is famously known as the cell state, and this is now what is known as the long term memory. The hidden state, it is also called as a short term memory. Now, that is why the name of this unit now which is there is known as the LSTM, long short term memory. Okay, LSTM unit. So, fine. So, now what does this each of these transformations does? Now, this is in common perspective, what does it does is this forget gate which is there, it decides now what old information that is there now you can forget. So, the input gate decides what new information needs to be stored, and then this candidate cell gate create the new candidate information, and output gate will say that now how much new information, it is combining the old memory and then the new memory. So, this is the colloquial way in which they say, but we need to look into them much more in a better way as a transformations. So, now let us represent this forget gate as F, this is I, this is C, and this is O, and these are for each timestamp. Now, what will be the output? Now, let us go into that. The FT and the input for this, so the input is at any given timestamp HT minus 1, CT minus 1, and XT. Now, these are the inputs that you have. Now, how do you go ahead and perform this computation of FT? Now, we use the sigmoidal activation. So, now you can think of a similar transformation. I will not be going ahead and mentioning the size of each and every matrix that are involved, weight matrices that are involved. Now, similarly, the way in which we computed for RNNs, you can go ahead and compute for LSTMs as well. Okay. Take it as a small exercise, it will be really helpful now if we can look into it. Okay. So, now this is now what is the weight that you are giving it for the input in the forget gate, that is what this term is, into xt. See, whenever I use this, now think of this as the dot product which is there, plus now what is the weight that I am assigning in the forget gate for the hidden state into ht minus 1 plus what is the bias term that is involved in the forget gate. Now, similarly, the outcome of input gate, that is also a sigmoidal thing. So, what is the weight that I am assigning for input x in the input gate into that input xt plus weight associated for the hidden state in the input gate into the previous hidden state, okay, plus the bias that is involved, okay, sorry, the bias that is involved in the input gate Vi. Now then similarly first we get this Ct tilde, now for which we use tan H activation. Now here what is the weight that is associated with X in this computation of candidate into Xt plus what is the weight that is associated with transforming the previous hidden state in the candidate state into the Ht minus 1 plus this Bc. Now using this, now combining the forget gate, input gate and the previous contexts, we get the current cell state. Now Ct is, you take this Ft, go ahead and perform element wise multiplication, the Hadamard product Ct minus 1 plus It into Ct tilde. See, since we are looking at a sigmoidal operation in the forget gate as well as the input gate, so you can you can think of sigmoidal operation as some kind of a percentage calculation. Now that gives rise to the famous way in which I told about forgetting input and all those things. So you can go ahead and look at in a similar fashion. Okay. So now we got Ft, we got It, we got Ct, we got. Now what is the output? Now the output computation is now OT is equal to some sigmoid into the weight that is associated for the input Xt plus the weight that is associated for the hidden state Ht minus 1 plus Do, okay, and final computation of this Ht that you want to send it for the next state, now which is OT, this taking Hadamard product of tan H of Ct. Okay. So now the way in which we can visualize this, now this is an LSTM unit. Now you get Ht minus 1 and then you get Ct minus 1. Okay. This is Ht, this is Ct, the input is Xt. Normally you can compute Yt also, in which the weight that is associated into Ht plus By. You can go ahead with the linear transformation and then do it. Now this will be the Yt. The same set of weights, see now there are lot of weights here that are involved. This is weight, this. Now you need to learn, here there are no weights here. Okay. These are the different weights that are involved in one cell. Okay. Now these weights are repeated across different for example, if you want for x1 also use the same weight, for x2 also use the same weight, for x3 also you use the same weight. Okay. So like that you go ahead and use the same weight. Now if you have layers, okay, if you have multiple layers, now then you will have different weights. For one layer 1 will have one weight, layer 2 will have a totally different weight. Okay. So that's how this LSTMs will work. Okay, that is what we are declaring here. So now you can see here the input size here is 3, okay, and the hidden state size is 8, the Ht size is 8, and then the number of layers that I have is 1. Now that means that it is a single cell that I am having. So and then batch first is true, the first element, that is the shape of 0, has to be the batch size. So now if you have this, so the input shape, output shape, hidden shape and the cell shape, so you can look into it and then exactly in the same way we perform the computation, now we can perform the thing here. Okay. So now let us look at another what do you call way in which sequences are handled, now using what is known as GRUs, known as gated recurrent units. Okay. Let us look into GRUs. GRUs, gated recurrent units. Now these are simpler than LSTMs for sure, okay, but it only has one state. Okay. So RNN had only one state, RNN had only one state, LSTM had 2 states, GRU has only 1 state again. Now let us look at how does the transformation happens here at GRUs. Okay. Now we have what is known as the reset gate. Okay, these are the famous, again similar to what we have in LSTM, these are the terminologies. Better to look at them as some transformations. So that would be a better way of doing it. So and then we have the update gate. This is represented by RT, this update gate is represented by ZT, and then now we have the final outcome, which is the hidden state. Now how does the transformation here happens? Now we go ahead with computation of this RT. Now we use the sigmoid, the weight that is associated with respect to x for in the reset gate into xt. So what is the input in this case? You have ht minus 1 and xt. Okay. Now the output will be so ht, and you can even compute yt similarly. Okay, fine. So then the weight associated with respect to the hidden state in the reset gate into ht minus 1 plus the bias term br. Now then we go ahead and compute this zt. Now this is again a sigmoidal operation. W x in the update gate into the input x plus W h z, the weight associated with respect to the update gate for the hidden state, into ht minus 1 plus bz. Okay. So now then we compute this candidate hidden state, now which is ht tilde. How do we do it? Now we use the tan h operation into W xh into xt plus W h hh, okay, into ht minus 1 plus bh. Oh, sorry, there's a very small mistake here. So WHH into this RT, which is there, taking the Hadamard product with HT minus 1. That is why it is known as the reset gate. Okay, you take the Hadamard product of this plus this BH. Yeah, fine. And then how do you compute the final hidden state? The final hidden state is 1 minus ZT. Now you can, as I told you, since the ZT is having a sigmoidal activation, we can think of it as some kind of a percentage. So taking the Hadamard product of HT tilde plus ZT, taking the Hadamard product of HT minus 1. This is how we compute HT, and then you can compute YT now, which is so YT is W H Y or YH. So we have been using, first we represent so YH, that is HT plus BY. So the way in which it looks similar to the RNN unit. So you get HT minus 1 and then you get HT as an output whenever you have given XT, and similarly you get YT here. Now the weights that are involved here are these will be matrices. Now these are the weights that are involved. We can perform the operation using these. Okay. So now let us look at that a similar fashion. So the input and output will be similar to what we had in the RNNs. Okay. So now let us use this and come up with a simple classifier. Okay. Now here the input dimension is there, hidden dimension and number of classes. See, to perform the classification, the way you need a fully connected layer. Okay. So what do you take? You take the hidden state, and then using that hidden state you apply a fully connected layer to the whatever is the outcome of that hidden state at the last instant, actually at the last instance. Now if you want it in each of the case, for sure you can do it at each instance. So and then you can go ahead and transform it into the space of whatever is R number of classes. Okay. So now LSTM input size is input dimension whatever you have given, hidden dimension, number of layers I have fixed it as 1, and then the batch first is true. That means that every first dimension has to be a batch. So LSTM, you pass it through LSTM, now you get 3 output whenever you do it in LSTM. Why? Now because it has 2 states. Now one is the hidden state, other is the cell state. Okay, you get the output hidden state and then the cell state. Okay. Now then what do? You take the last hidden value which is there and then pass that last hidden value into the fully connected layer to get the logits. Okay. So here you are defining the instance of the classifier. So input dimension is 3, hidden dimension is 16, and then the number of classes is 2. Okay. So then you are creating X now, which is 8 examples are there. Each example have 5 sequences, and each sequences is of input dimension or embedding dimension which is there is 3. So when you pass this, so you get for each of the 8 examples in the batch, you get 2. Number of classes you have declared it as 2, so you get a probability vector of size 2. You can use just 1 and then pass it through sigma, that is also perfectly fine. Okay. So it is up to you to way in which you handle this, that is perfectly fine. Okay. So now let us take a very simple toy data set and then try to work around with this. So now what is that I am doing is, now if the sum of the sequence values is greater than 0, then I will say it as class 1, now else I will say it as class 0. This is a simple data that I am taking. Now as we discussed earlier, now any custom data set that you want to come up with now has to be a child of this data set. Okay. And then you need data loader to go ahead and create it, fine. So then the number of samples, I am having 1000 samples, the sequence length. Okay. Now for each of the sequence I am there will be 10 sequences. So in one X there will be 10 of them, and each of that X1, X2, X3 will be of dimension 3. So that is what you are generating it in a random way. So number of samples, sequence length, input dimension. So and then you compute the sum of the first and the second dimension. That means you take the second and the third. So if you have x1 x okay. So now rather than showing it, it is better to write it. Now each xt now which is there has 3 values. Now what is he doing is, now he is taking these 2. If the sum of these 2 is greater than 0, it's greater than 0, now then now y is equal to 1, else y is equal to 0. This is what is being done. Okay. So now then if the sums are greater than 0, now then you go ahead and convert it. So this is a relational operation. So you will be convert, either it will become 1 or 0 depending on the outcome. Okay. And the length and then the get item, you have to define it anyhow. Now this is the data set that is being created. So you have created the data set and then you have to create the data loader. Now the batch I have taken it as 32, you can increase the batch size for sure, no problem. So you can see that, so each 32, 10, 3, okay. This makes sense. So this is our input. Now then create a classifier. Now the input dimension is 3. So each xt will be of 3 dimension. Hidden dimension I am taking it as 32. So number of classes I am taking it as 2. The loss I am taking it as nn dot cross entropy. Okay. So I am using Adam optimizer with 0.001 as the learning rate. Okay. And the same good old story. So you are doing it for 10 epochs. You take each batch and do it. Same story. Whatever we did, any classification task which is there, whatever we did for CNNs or images or MLP, the same good old story is what we are trying to do it here. As you can see here, over the epochs, we can easily see that the loss value is decreasing, and then we can see an increase in the evaluation metric, which is the accuracy in this case. Okay. Now this is how we work with the sequences. Okay. So now let us see how we can save the model. Okay. See, what do we mean by model is the weights that are there. So, whenever we mean by a model, we actually mean these weights, whatever these weights are there. Now, this is what we mean by the model. Now, these weights will be stored. Now, say that you want to infer sometime later. Now, rather than at that point of inference starting afresh from the random initialized weight, you can use these weights and then just do the inference. Or now you have already trained model on one specific task. Now, if it is something similar, you can take those pre-trained weights which are there and then only fine tune it later. Now, these are the options which are there. Now, therefore, saving a model, in a sense saving all these weights, is very much important. Now, let us see how that can be done. Now, we use this torch.save. Now, we use all these parameters which are there in this particular path, LSTM classifier.pth. pth is the extension that we will be using. Okay. Now, you can specify the path, or you can just specify just the file name. So, here what will happen is in the current working directory, now it will be saved. Now, if I run this, you can see here in Colab that here you can see this being saved, all the weights being saved. Okay. Now, you can then what you can do is you can create an instance of the model and then you can load the weights. Now, this is what you created an instance. Okay. See, whenever you are creating an instance, now whatever model you have saved now with the same parameters. For example, here now this classifier was having 32 as a hidden dimension. Okay. Now, you create an instance with 35 will not work, or input sequence input dimension is 5 will not work. Okay. Now, because there will be an incompatibility with the weight matrices during its transformations. Okay. Now, those things needs to be taken care. So, we have created an instance and then you have ported on to the device, and then what did you do? So, loaded model dot load state dictionary. So, what are you loading? Torch.load from this specific path which has been specified. You look at this LSTM classifier.pth file which is there and load it, and you port whatever has been these weights that are there onto the device. So, map location is equal to the device. Okay. This is what is being done, and then loaded model. So, you are putting it in the evaluation mode. Okay. So, this is how you load the model. So, yes, model loaded successfully. Okay. So, now this is how so it is not specific to the sequences. Now, you can do it in a similar fashion for CNNs and other things. Okay. Now, later in the next section of the tutorial, now we will be looking now how we can get these kinds of preloaded models, pre-trained models which are there, and we can load them. Okay. That we will see it in the next tutorial section. Okay. See, till now, if we go back and look at all the code, we have been rewriting the training loops and the evaluation loops. For the classification task, so most of the times it will be same, the whole procedure will be same. Now, what do? You perform the forward pass, get the logits. Now, once you have the logits, now then what do? You compute the loss. Now, once you compute the loss, you clear off the gradients which are there, and then compute the gradients newly for that specific instance, for that specific batch, and then perform the weight updation. This is the standard thing that we do. So, now we can make it into a reusable training functions. Now, this is for one epoch. That means that you have to call this function which is there for how many epochs that you want to go ahead and train. So, model, data loader, criteria, optimizer and device. Now, these are the standard things that are needed, and then the remaining code is exactly the same. So, first you have putting it in the training mode. So, and then you have bookmarkers for total loss, correct and total, so that you can compute the accuracy. So, and then you iterate over the data loader, you get for each batch of inputs and targets, you port them onto the device. Okay. And then you pass this inputs to this through this model and get the outputs and targets into the loss function, get the loss, clear off the previous gradients, compute the gradients for this specific batch, update the weights, so as per the gradients computed, and then update the bookmarkers, total loss, predictions, correct and then total, update the bookmarkers as discussed earlier. Okay. And then average, loss and accuracy are there. Now, you can return it at the last. Okay. So similarly you can have it for an evaluation also. So evaluation does not need optimizer, okay. So model, data loader, criteria and device. So model dot eval, so again bookmarkers. So you put all these things in with torch.nograd, so that inside whatever is happening inside this, you do not need to compute the gradients. So then you iterate over the data loader. For each batch you first port them onto the device, obtain the logits and then the targets, pass it through the loss function, get the loss, just keep the loss as the bookmarker, get the predictions, update the correct and total, and then finally compute for the whole data loader which is there, for all the examples in the data loader, compute the average loss and then the accuracy, and then you can return it, okay. Now this you can reuse it for any kind of classification tasks that are there, okay. So now we will be using it in our next section of tutorials. Now just to give you a recap on what are the things that we just discussed, we in these sections of tutorials, starting from understanding tensors, working with CNNs and then in RNNs, now we have looked tensor creation and then how to work with the different shapes of the tensors. Now tensor indexing and reshaping, so moving a tensor to GPU, so automatic differentiation and working with gradients. So working with NN dot modules, all its NN dot linear, NN dot con 2D, NN dot RNN, NN dot LSTM, NN dot GRU, different things. Working with linear models, loss function and different optimizers, we looked at MSE loss, we looked at cross entropy loss, and different optimizers like SGD, ADAM is what we have seen. Similarly, we can look at RMS prop, ADAM W and things. Now creating a custom data set or loading the data from the existing PyTorch library, we saw that. Implementation of MLP, now we saw. Implementation of CNNs, we saw. RNNs, GRU and LSTMs implementation we saw, and then we looked at reusable codes for training and evaluation loops, and then we looked at how can you save the trained weights and then how can we load them, okay. So now the students are ready for advanced deep learning topics, okay. Now with this we conclude today's tutorial discussion. I hope you enjoyed, and then now you are capable of writing your own neural networks using MLP, CNNs and RNNs, okay. In the next section of the tutorial we will be looking at how can you load the pre-trained models like VGG, like ResNet, so ConNext, so different models we will see their architecture, and then we will see how we can go ahead and load those weights and then tailor them as per our need. Now we will be working with MRI tumor classification problem, and then we will be going ahead with that. I hope it was informative. Thank you all for patiently listening. We will meet in the next section of the tutorials. Thank you. Bye bye.